Okay, so this is our sort of part two to reverse chain rule. So I'm going to say now that I think the harder bit was before, in the sense that you've covered the content. So I'm not actually going to be so much teaching you anything new. There won't be any new tricks or anything like that. All it will be is some slightly harder problems. So I'm going to be doing a couple of examples, and then you can try a few harder problems. So because I won't be needing as much time to actually be telling you stuff, I'd really like you to have a go at this, try this now problem. Give yourself at least a few minutes to attempt it. Maybe you'll get it quickly, or maybe you'll get stuck. But give it a genuine attempt, because you're not gonna have lost that much time, and you won't need a sort of full lesson's worth to get through the example, I don't think. And this is quite a nice little problem, if I do say so myself. I did make it up. So give it a go. You'll need to think about using reverse chain rule, but perhaps initially you might need to make use of some log rules that you know of. It should be within your ability, but see how you do. And perhaps you might have a method that I didn't think of. So give it a go. You can pause the video now. Okay, so here's what I'm thinking as a way to do this. We're going to integrate 1 over x ln x to the 8. Now, we know the derivative of ln x is 1 over x. So this almost looks a bit like a function to a power multiplied by its derivative, but it isn't quite. We need to tweak this a little bit. This is the same as 8 over x ln of x, first of all, right? No integration or differentiation. It is just equal to that. Because I've got something with a power on the inside, I can take that power to the outside of the logarithm. And now, notice, if I just make it a bit more obvious by putting the 8 there, this ln x, this is effectively ln x to the power of 1, right? Which is what it is. So you can almost think of this as a constant multiplying a function to a power multiplied by the derivative of that function, right? Derivative of ln x is 1 over x. So we can use reverse chain rule here, and we're going to do as our initial guess then. Let's try ln of x, and then we add 1 to this power 1. So we're going to turn it into 2. And what do we get? The 2 comes down. I get ln x to the power of 1 again. Then I multiply by the derivative of ln x, which is 1 over x. So we get 1 over x ln of x, which is almost what we wanted, right? It's almost this, except it's a 2 instead of an 8. So let's multiply everything by 4. I'll put 4 here, then 4 here, 4 here, which effectively makes. So this is effectively 8, and we've done it. This function here is what we started with, except it is exactly what we started with, right? Just a different form. And therefore, if we were to integrate this, we would end up with 4 ln x squared. So let's make a note of that here then. The integral of 1 over x ln of x to the 8 equals 4 ln of x squared. And then the reason I like this is because you can actually, I wouldn't necessarily call it simplifying, but you can convert this into an even, perhaps you could argue, more beautiful form. So it turns out the integral of this function, if you get that using reverse chain rule, we can actually go a little bit further and consider this. If you've got two square numbers multiplied, you can put them inside the same squaring operation. So here you've got 4, which is a square number, and you've got ln x squared, which is of course a square because you've got the square on the outside. So this is actually just 2 ln of x all squared, right? Same thing. And then on top of that, this 2 on the outside of a log can go onto the inside. So I would argue the nice way to represent this final answer is it's the ln squared of x squared, right? And that's our final answer. That integral is the log of x squared all squared. Okay, so let's look at our first example so we can start getting into the swing of things. It might be tempting to think, oh, it's a fraction, so it must be the fraction version of the problem, but you can quickly dispel that suspicion by thinking to yourself, well, if I were to differentiate the bottom, I would get 3 times 2 plus cot x squared, and then multiply that by the derivative of 2 plus cot x. It's not going to end up looking like the top. So we're not going to use the ln version of reverse chain rule. Instead, notice that we can rewrite this as follows. This is cos x squared x times 2 plus cot x to the power of minus 3. And if we have in the back of our minds the derivative of cot x is minus cos x squared x, let's make a note of that, then we should be able to find the derivative of this thing. So 2 plus cot x has the derivative of, well, 2 goes to 0, and cot x goes to minus cos x squared, which we've got on the outside here, except for the minus. So what that means is this is indeed a scenario of a function to a power multiplied by its derivative. So let's try doing our guesswork sort of game again. So let's take the derivative of the function, but increasing the power by 1, so it goes to minus 2. And now we just do our usual chain rule. Minus 2 comes down. We've got 2 plus cot x, take away 1. And now we multiply by the derivative of 2 plus cot x. 2 goes to 0, cot x goes to minus cos x squared x. So we end up with those minuses cancel, the minus 2 and the minus cos x squared, and we just get this. And now we tweak, so I'm going to put a half over here and a half here, and then a half times 2 means that that 2 goes away, and look, we've got it. That is what we wanted to begin with, so therefore we've got the answer. It's 1/2 2 plus cot x to the minus 2, and probably you'd want to write this a bit more nicely as 1 all over 2 times 2 plus cot x squared. Cool, and we found the integral. Let's look at one more example. Oh, and plus c, don't forget. Okay, so then let's look at this one. So this is the first time we're doing a definite integral, which doesn't really change the problem too much. So let's focus first on just that expression, 5 tan x sec to the 4x. Right. So I think this is one of those questions where it's almost, it kind of shows the sense in which some people can really like maths and some people can really not like it, because this is almost like a bit of a puzzle, a bit of a riddle, where there's no rule, you just have to kind of spot the cleverness. So perhaps your first instinct is you think, okay, sec to the 4. I know sec and tan are related in many ways. For instance, I know that the derivative of tan x is sec squared. I know that tan squared plus 1 is sec squared. The other one to keep in your mind is also, though, the derivative of sec x is sec tan. So the trick to this one is to split it up in a way that might not immediately be obvious. Sec x, tan x, sec cubed. And now we notice, okay, this expression, it's actually sec x to a power multiplied by the derivative of sec x, because again, this should be sort of in our memory. The derivative of sec x is sec x tan x. So now we can do our guess, right? We're going to do the derivative of, instead of sec cubed, we raise it to a power, sec to the 4. And let's do the differentiation. We get 4 sec cubed x multiplied by the derivative of sec x, which is sec x tan x. So then it becomes 4 sec to the 4 x tan x. And we almost got what we want. The only thing is we need to insert a factor 5 over 4. So we add 5 over 4, and then we end up just getting exactly what we needed, 5 sec to the 4x times tan x. So that integral is 5 over 4 sec to the 4x. And then what are we told? We're going to then just finish this off. So we'll take the limits, and that's apparently equal to 15 over 4. And now we just do what we normally would do, work this thing out. So let me just clear some space. Oh, I thought I paused it, sorry. You just had to watch me do that. Hopefully you skipped. So we've got 5 over 4 sec to the 4 of theta. And then what's sec of 0? Well, cos of 0 is 1. So sec of 0 is 1 over 1 is 1. So it's minus 5/4 equals 15 over 4. Let's multiply by 4, divide by 5, and we'll get sec to the 4 theta minus 1 equals 3. Sec to the 4 theta equals 4. Therefore, sec squared equals 2. Sec squared theta equals 2. And therefore sec theta equals plus or minus the square root of 2. Therefore cos theta equals plus or minus 1 over root 2. And then just keep in mind the fact that theta is in that range, and you should be able to solve that one. Theta is equal to, in this case, pi over 4. Cool, and that's how we do it. So the main trick there is spotting that sometimes you can split apart these functions. So you do need to have these in your head, the derivatives of the standard function. Otherwise, you might trick yourself into doing the wrong thing, such as thinking, oh, I don't know, the derivative of sec is tan, and then you use the power 4. But the trick was to turn it into a cubed and take that sec out, so we could get the correct derivative being multiplied. Cool, so let's try some questions. So I'll just get you to do these, just one slide, so I don't think it's too many. see how you do. See if you can do these. If you do feel like you need an extra challenge, feel free to ask. But I think that should be sufficient, because then you've finished all the examples, all the practice questions for that chapter in the book, which I think is reasonable. It's a reasonable place to start. You can always have a bit more difficulty in the homework. So see how you do. Pause the video. Let me know if you need any help.